the Quaternion drive. And part of what I need to do is explain, of course, what I mean by the Quaternion drive. Basically, it's sort of an idea that's been bouncing around in my head to solve one of the problems that we've been seeing coming up again and again, where it's inspired by how you can interpret a quaternion. And also, quaternion is such a cool name, I just had to use it. So, and usually the most comments I get under that is like, well, why didn't they just use a ball and socket joint? And it's like a really valid, really good question. Why don't we use a ball and socket joint? So I was rather surprised when last weekend this comment came up underneath it, which was not one that I was expecting. And I'll blow it up so we can go ahead and look at it. And this is from P&D Robotics, which is, one of my sort of favorite humanoid bot companies over in China, because they've really done a lot of out of the box thinking on how they put their humanoid together. So I really like following them. Um, and he says, we are bone socket designed for a second generation of Atom robot. Now, I think by bone socket, he actually means ball and socket, since it was like kind of in reference to what it said up there. I hope it's not bone and socket, because that usually means it's a tooth extraction not done correctly. Okay. The idea of this is, imagine I'm going to just go ahead and take this and then kind of break it apart. So imagine you have a cup down here, and here you've got a ball, which is typically how you would make a ball and socket. And then imagine you have a servo drive right up here, and that you take that servo driver actuator and you actually put it inside of the ball and the ball inside of the cup. Okay, so that's what we're going to do. We're going to go ahead and take these and kind of pop them back in there. And you can see in the backside down here in the South Pole, we would go ahead and this is where we run our cables and power and everything else that would need to go to that actuator to get that to work. I tried printing out an actual version of this for today. Yeah, yeah,
Oh,
yeah.
okay. I was about to ask that.
And it took me like 4 days just to get to here. And I decided that was like too much. And already we're seeing it's bigger than a grapefruit. Well, um, remember this mechanism here that we've seen an Optimus wrist and that we've also seen in iron from Xipeng. That is a parallel mechanism that's able to get like two rotations out here in the wrist. But remember, this whole thing rotates around here. So basically, it rotates first and then it does the business down here. And I was thinking, what if you turn this wrist around? What if rather than having the rotation of the wrist happening first, what if you had it last? Could you come up with a mechanism to do it? So once again, just to remind everyone what this mechanism looks like, um, as the two of them go together, you end up getting a pitching, and as they go in opposite directions, you're able to get the yaw, and you're able to get that to move around. So that's one way that it works. So let's see, is there some other way we could do it? And this is where we come to what I think the quaternion drive is going to look like. And so here's that motor that I was thinking of putting inside the ball. So again, the same idea is we get an actuator here, and what we want to be able to do is point that actuator in any direction. So what if we take that mechanism here and start thinking about doing that? So what you would do is you would just go back and forth like that, and this will give you abduction. There's your abduction. Okay. Now then, we have the other way that we can go, and that is like back and forth like this. This one here actually comes from Medea, which you may know as the world's largest appliance manufacturer of dishwashers and microwaves and other things in China. And also here is the Aptronic Apollo. So they're using the same actuation strategy, but you'll see they don't actually have a Heim joint here. They've got something different there. And that actually allows them to have a much greater range of motion. So let's take this idea and see if we can incorporate that in and make a modification to it. So that's what we're going to do now. But when you decide to go this way,
Oh, yeah.
you can really go. Now, the problem is the conflicts that are happening elsewhere. For now, I found a second reason that Optimus will suck at soccer. The first one is that because it didn't have the head movement back and forth, it will not be able to do headers the way Ronaldo is able to. Look at the robot and look at the human. Can you see how the human is kicking the ball
Yes.
and how the robot is kicking the ball?
It
Okay.
is straight, like the robot straight angle a little bit.
Yes. Okay. So the human is basically kicking it the proper way. Maybe it's not, the perfect form, but it's what you're supposed to do. They come through like that. Now, guess what happens with Optimus? Okay. Hello, Mara. How's your weekend been?
Well, it's good. How are you? It's good. Yeah.
Good. Yeah, I'm having some work downstairs, so it sounds like a dentist office or something like that, or some drills going on. That's what it's about. But yeah, so we're ready for kind of an episode I've been waiting to do for a long time because there's a foundation we've had to build to make sure we have a little bit of theoretical groundwork there and some understandings. And so the name of this episode is the Quaternion drive. And part of what I need to do is explain, of course, what I mean by the quaternion drive. Basically, it's sort of an idea that's been bouncing around in my head to solve one of the problems that we've been seeing coming up again and again, where it's inspired by how you can interpret a quaternion. And also, quaternion is such a cool name. I just had to use it. so, so we went ahead and do it. So, what exactly am I talking about, and how have we got here? And if if we remember a few weeks back, I put out a post that was about how the hips work and the robotic hips and trying to classify the different ones out there, the ARF structure, the FAR structure, all those. And I've talked about at length how the human body is a ball and socket joint, yet all the robot manipulators are using these stack serial actuators to do it. And usually the most comments I get under that is like, "Well, why didn't they just use a ball and socket joint?" And it's like a really valid, really good question. Why don't we use a ball and socket joint? So I was rather surprised when last weekend this comment came up underneath it, which was not one that I was expecting. And I'll blow it up so we can go ahead and look at it. And this is from P&D Botics, which is, one of my sort of favorite humanoid bot companies over in China because they've really done a lot of out of the box thinking on how they put their humanoid together. So I really like following them. Um, and he says, we are bone socket designed for a second generation of Atom robot. Now, I think by bone socket, he actually means ball and socket since it was like kind of in reference to what it said up there. I hope it's not bone and socket because that usually means it's a tooth extraction not done correctly. Okay. So I think they really mean a ball and socket. And that's kind of big news. And it's like kind of curious. Wow. How are they going to do that? How are they going to pull something like that off? And so let's sort of go in and figure out what's going on. And, the short answer all along is like, why don't we have ball and socket joints in our humanoids? And the answer to that is they're really hard to actuate. Figuring out an actuation strategy is very difficult, which is why we've kind of gone to this other approach. So to sort of solve this whole thing, we're looking at what is the human hip joint and kind of the current state of the art. This is an example of how Adam has gone ahead and set it up as serial stacked actuators. That what would it take to actually make a ball and socket joint? So let's go through there and see if we can come up with a solution to the problem, or is it still something that is very challenging and that we need some other thoughts or some other ways of doing it, and how might they be doing it, which I think will be kind of interesting. But before we do that, let's just remind ourselves of the previous episode where we talked about the singularity and how this has kind of helped to set everything up that we're going to be doing in this episode. And that is the singularity, as we all know, is a result of somewhere in one of your functions, there's the result of you having to divide by zero. And you never want to divide by zero. And usually means there's something going wrong with your function around some point. And typically in robotics, that has something to do with rotations. Okay. So the functions that you come out from being able to describe rotations in space, a lot of times when you try to solve them, there may be a location where you're doing a divide by zero. So a quick primer, the full-blown primer, previous episode, go and look at singularities, and we will go through it in a lot of detail. But just as a reminder, there's one way of describing an orientation in the space with respect to something else. And this is the standard yaw pitch roll, which everyone has heard of. It comes from aeronautics, and we refer to as a roll, which is kind of a left to right. You're turning direction to pitch up and down in your roll, because spinning over something you don't want to do. And these can be described mathematically as like a rotation about the x-axis, about the y-axis, and the z-axis. And the order of operation and everything for yaw pitch roll is something which is very, very important. If you change the order, you will get a different result. So that's the first thing I want to kind of point out is that the last time I went through trying to show how different orientations result, and it took like 3 or 4 takes, which hopefully you cut all those out before I get it right because I was screwing up my right hand rule and using a left hand rule and everything else. So what we're going to do right now is I'm going to go ahead and show live how we can compare different yaw pitch rolls and exactly what the idea is of yaw pitch roll in different context here. So let me go ahead and now share my other screen here, which is going to be this one right here. And so what we can see is we've got two coordinate systems where Z is up, it's blue, X is red, and green is the Y direction. Now, red usually means yaw, green is always pitch, and roll is always in the blue. And over here, I'm going to type in some numbers, which will tell us exactly, I want it to yaw right now. So if I say 90 degrees yaw, you'll see they both do the same thing because they both rotated about the X axis. Now, one of these actually does yaw as the first rotation, the other one does it as the last one. But because the other two are zero, it's as if they're not there. So you get the same result. So in this case, whether it's yaw pitch roll or roll pitch yaw, you're going to see the same thing. But as soon as we decide to put in another rotation in the middle, you'll see they're pointing in different directions. And then if we make them all exactly the same, 90, 90, 90, you'll see they do end up different. Only the Z ends up kind of pointing in the same direction, but then the Y and the X are in opposite directions of where they're supposed to be. So that's why order is very important when we go through looking at yaw pitch roll and being able to describe orientations. So the idea is 3 values and 3 operations that have to be done to describe any sort of orientation space. So that's one way that we can represent it. And it's the most compact version of orientations because it's just 3 values that you're using. And however, you have to go through these 3 different operations. So while it's a very simple way of being able to describe an orientation, it has inconveniences. And one of the inconveniences is something called gimbal lock that around certain orientations, it's very hard to transform or use your yaw pitch rolls. So it's basically a notation, but actually you can't do very much with a notation other than describe something. So it's very hard to use them to transform things or to start stacking them together. It becomes a bit complicated. So what I will now do is we're going to kind of go back to the next kind of ways of being able to represent orientations. So let's go ahead and take a look at Cartesian coordinates first. So when we think of Cartesian coordinates, this is something we're familiar with, that I can describe any location space as, X, Y, Z location. And if from that location, I want to move to another location by some delta, which would be, X2, Y2, Z2, the new location is just the addition of those components. It's very easy to do that with Cartesian coordinates. Very, very simple, nothing complicated with that. With yaw pitch roll, you can't do that. So even though yaw pitch roll may look very much like Cartesian coordinates, if you go through this whole thing, I'll say, well, I've got this yaw pitch roll and I want to do another yaw pitch roll on top of that thing, you just cannot add the two values together. It doesn't work that way. So the question is, okay, then how do you find the new yaw pitch roll from what you currently have? And this is where we have to introduce this idea we had last time of actually using what is known as a direction cosines matrix, where it's a 3 by 3 rotation matrix, where the I, J, and K represent the new directions of your coordinate system. So if you look at this frame up here, you'll see the big frame is like the world coordinate system, and the smaller one is my new orientation space. And the direction of the little red axis here is basically I. So if I know what the I is, and these are unit vectors, I can draw it very easily. It's going to point in that direction. Y is going to point in this, and Z is going to do that way. So that's how that works. And it's very convenient because it turns out you can transform objects and everything once you have this information and do a lot of really useful math with these cosine matrices, direction cosine matrices, as opposed to yaw pitch roll. So how do I go from one yaw pitch roll to the other? Well, before you can do that, you have to know how do you transform yaw pitch roll values into one of these direction cosine matrices. And since yaw pitch roll in this case, if I'm saying yaw pitch roll, I mean X first, then Y, and then Z, is basically a rotation about X, then a rotation about Y, and rotation about Z. And these are well-known kind of matrices. You just multiply them or concatenate them together and you get this. So in other words, if I want to create that direction cosine matrix, all I have to do is plug in my yaw pitch roll values into the appropriate places here. And great, I can generate what that matrix will look like for that particular set of yaw pitch roll values. Okay, so let's imagine I have the two yaw pitch roll coordinates, 5, 10, and 15. And then from there, I want to rotate an additional 20, 30, 40 from that current location. How do I do it? Well, you got to follow these arrows. You're going to take the first one, plug it in to that formula I showed you, and generate this matrix. Then you have to do it with the second one and get that matrix. And now that you have both of them, and you got to do it in the correct order. This one is first and that one is second. You then have to do the matrix multiplication together. And we're going to show how that works in just a bit. And then come up with this new matrix over here. Now, the new matrix of values, you have to then go in the opposite direction to turn them back into yaw pitch roll, which means you kind of have to solve these equations. And this is basically how it looks like. So you have some sines and some arc sines and arc cosines. Some people may realize you could actually get away without having to calculate the cosine here, because basically they kind of cancel each other out when the tangent function takes that fraction. But that's just kind of shows you the math you have to go through to get it. And when you do it, you'll see the numbers I come up with here are not the same numbers as if I just added them together. Now you might be saying, oh, well, they're kind of close. And like, I was actually surprised how close I got here. And it's mainly because I chose kind of small values here. If you choose bigger values or more random values, it doesn't even resemble the other one here. So this just kind of shows you that what you have to go through to be able to just add these two together. That's a lot of math to be able to get yourself there. Okay, so right now we've looked at two ways that you can represent an orientation space as yaw pitch roll, and you can also do it with the orientation matrices that we saw. These, but there's another method of being able to represent it, and this is something called axis angle. So with yaw pitch roll, we have to go through three operations. We have to rotate about the X, then about the Y, and then about the Z to be able to reconstruct the orientation that we want to have. And these are rotations about the principal axes, X, Y, Z, of course. But there's another way that in one operation, you can rotate from one orientation to any other orientation in space if you select your axis correctly. And that's the trick. But there always exists some axis W, and this is being represented as a unit vector pointing in space, not necessarily along a principal axis. And if you rotate about some value theta using the right-hand rule, you can move from one to the next. And we're going to see that in just a minute. But conceptually, that's the idea. It's one more piece of information that you have to send as opposed to yaw pitch roll, but it's only one operation in a sense. It's very easy. You're just doing one rotation rather than having to do multiple ones. So this is like the third way we're looking at it. Now, appropriately, there's a fourth way of doing it, which is called the quaternion, okay? And the quaternion is called that because it also has these four terms that are in there, where A is known as a scalar term, and then B is known as kind of like the complex terms or the actual vector that things are rotating about. Now, these IJKs represent directions, like X, Y, and Z, but they also represent imaginary numbers, which means they use imaginary kind of rules as far as multiplication and everything else, which is very fundamental and important to the way the quaternion works. Basically, it's the trick of the quaternion. But conceptually, you can think of it as very much like the axis angle, in that you have a direction that you're pointing in space, and you also have a scalar amount, which sort of represents how much you're supposed to rotate about it. Except it's not as explicit as it is with the axis angle, where A is not the actual angle itself, but it's the cosine of the angle divided by 2. Okay. But in a sense, you can conceptually think of that as an angle and a direction in space everything's going. But the quaternions have one other property, and that is, in order for this trick to work, the magnitude of the quaternion must be 1. And that means all four values, not just the direction vector. So the direction vector is not necessarily a unit vector if A is non-zero. The whole quantity has to be. And that basically means the sum of the squares has to equal 1 in order for it to be correct. So a lot of times when you create these quaternions, you may have to normalize them to make sure they're correct. So that's the fourth way. And there are ways of being able to go from quaternion space to axis angle space. This is basically, like, again, I'm saying the relationship between theta and alpha is pretty straightforward. And the relationships between the two vectors you have there are pretty straightforward. It's just a different renormalization that you have to go through because you want to have a unit vector. And so it's pretty easy to move between the two. They're conceptually the same thing. It's just that quaternion has, like, a better kind of ring to the name as opposed to axis angle. And now what we're going to do is we're going to jump into a live demonstration to actually see how all these four different types of representations of orientations relate to one another, how we can use yaw pitch roll, how yaw pitch roll is able to create a matrix, what those matrices look like, also what the equivalent axis of rotation would look like, and the equivalent quaternion. So what we're going to do now is we're going to leave this presentation and we're going to jump into the live demonstration. Okay, so now what I have here is a simple coordinate system where I'm going to show pretty much the four different ways of being able to describe an orientation in space. And I'm going to put in yaw pitch roll values. I'm going to see what the resulting matrix values are, axis angle is, and quaternion values, just so we can have an idea of how they relate to one another. So the first thing I'm going to do is just rotate about 45 degrees about yaw, which means it's going to be an X rotation. And when this happens, I can see the original coordinate system, which is kind of transparent, and the new position, which is solid. And you'll see this other kind of white coordinate system or arrow, which is superimposed over the red. And that's indicating the single axis rotation. That's the axis you would have to rotate about to get this orientation in one shot. And that makes sense. It's pointed in the X direction because that's all we did. We only rotated in the X direction. And now, if we try to generate a rotation matrix out of this, which we'll see over here, we'll see that the I direction, the X direction, is still pointing in the same direction. It's 1, 0, 0. So it's pointing off an X. But if we look at J and K, which represent Y and Z, we will notice that sure enough, the Y is no longer pointing purely in the Y direction. It's lost a little bit. So it's about only pointing 70% that way. And it's now pointing 70% kind of up in the Z direction. And those numbers are exactly the numbers that you see when you take the sine or cosine of 45 degrees. And then if we look at the Z, we get exactly what we expect there as well, is that it's kind of pointing in the Y, but in the negative Y direction. And it's lost a little bit of the component pointing up on the Z. So that makes perfect sense. Again, if we want to represent this as an axis angle, in other words, what's the direction vector that you rotate about? We'll notice, well, it's saying just the X, there's no Y or Z component here. And it's a 45-degree rotation. No surprise. That's exactly what I did. We expect that. But then we come down to the quaternion and you look at those numbers and you're like, okay, what does this mean? And it's kind of hard to tell. I mean, you can look at B, C, and D, and that's telling you, oh, it's pointing in the X, but it's not in unit vector form. But still, it's pointing in the right direction. This number here is a bit crazy because that sort of represents the rotation angle. But remember, it's the cosine of the angle, which is why it's weird. And what ends up happening is that the smaller the number value of the rotation you have, the bigger A gets. So the more your rotation goes to 0, the more A goes to 1. And the bigger your rotation gets, the smaller the value it gets, which is kind of counterintuitive. And then you got to remember this whole thing the sum of the squares of these has to equal 1. And this is kind of why the B value here is kind of very small because the A value is very big. So if I do something like say, oh, I'm only going to rotate like 2 degrees now, you'll see the quaternion is like almost a value of 1. I mean, that rounds basically to 1 there. And the B has a very small value in X. So it's kind of hard to figure out. And then if I go to like about 90 degrees, we'll see that this kind of surprises you. And you look at that and say, wait a minute. Is that 45 degrees? Oh, no, it's not. It's 2 times 45 degrees. That's kind of how you get it because the way everything works. So that's sort of what's going on there to give you an idea of the different representations. But now let's get a full understanding of what's going on with being able to rotate about a single axis. So I'm going to put in some random numbers here, like 60, 30, and 45 in there. Okay. And so we can sort of see what these numbers look like. And you get an idea where the X is. And if you were to freeze everything here, oh, let me get my that back up. Let me stick that up there so it stays permanent. You can see that what these numbers are, and you can try to confirm yourself if you freeze the video and look at the matrix here, convince yourself that the ijk's are consistently pointing in the direction that you expect that they would be in. And now this white vector that we see coming out here, that's claiming if we rotate how many degrees here? About 83 degrees about this axis right here, then we should be able to get the coordinate systems to line up. So that's what I'm going to do right now is I'm going to take this and I'm going to rotate the original coordinate system around there. And once the arrows kind of match up and get to the exact same spot, you'll see, sure enough, everything overlays like it's supposed to. So we can put in any numbers that we want. Maybe there's like a minus 30 here. So it's going to be off some other direction. And sure enough, rotate yourself around there. In this case, like over 100 degrees, boom, we get ourselves in there. So these are different ways of representing orientations. Now, if you and I were going to be communicating orientations of things over smoke signals, which is very, very slow, we would probably want to just send the yaw pitch roll values because it takes, just 3 values is already enough. To have to send you a 4th value or to send you a matrix, which is 9 by 9, it's a lot. And on the other end, you can reconstruct it because maybe you've got a calculator, a computer, and you can put those numbers in and calculate it really quickly. So in many cases, if you're communicating over a long distance, that might make sense for being able to represent it. But when you actually want to do work with it, yaw pitch roll is of almost no value. You have to turn it into one of these formats to basically do useful work with it. And so that's what we're going to start to explore now is what happens next when we decide to go ahead and look at um, the work that has to be done and how we do these conversions from one system to another. So back to the presentation. Now we're sort of done taking a look at what goes on here. The first thing is I want us to understand is that almost the best format to use are 4x4 matrices, in which case the 3x3 upper part is the orientation. And then you add one more row to it and you get the positional offset. But we're only going to focus on orientation right now because we're trying to do an apples to apples comparison between rotation matrices and quaternions. So this is definitely the best, the handiest one to use. The only downside with it is we need 9 pieces of information that we have to always hold on to. And when we do the multiplications to get like the new orientation, this is what we have to do. We have to take this red row here and then do a dot product with this column here just to create that blue square right there. And we have to do it 9 times throughout. So what that means is that for each cell, there's 3 multiplies and 2 additions. Total of 9 cells, it's 27 multiplies and 18 additions per matrix concatenation. So that's a little bit of work. Now for quaternions, if you want to find out how to go from one quaternion to the next one and what that value is going to be, it turns out you have to do quaternion multiplication. And the multiplication is just like the standard polynomial multiplication that you used to, where you do the FOIL and everything else. The difference is we're dealing with complex numbers. So when I multiplies with I or J or K, you end up getting -1 because they're complex values. And it turns out I times J gives you K. Okay. And J times K gives you I and Ki gives you J. And it's non-commutative, meaning Ji is minus K where Ij was K. And that's also an important property because orientation matrices are also non-commutative. The order of operation is very important. So if you work this thing out, that means the scalar part, which is A, will just be equal to these. The I component is this, the J and the K, and we can kind of look at this and get an idea, well, how many operations are involved there? And we can see for each new term that we produce, there's 4 multiples and 3 additions. And since there's 4 terms, there's 16 multiplies and about 12 additions. Okay, what that means, if you kind of compare 16 versus 27 multiplies and 12 versus 18 additions, that's about a 40% savings in computation, to say nothing of the space and everything else that is saved in there. And it's not really a big deal now, but about 30 or 40 years ago, it really was a big deal to be able to do that. And we're going to sort of discuss the rationale and the reason behind that. And that is, if you go to Wikipedia and you look at quaternions, it goes back to Hamilton. and like this bridge where he got the idea that it's engraved on everything else, and it really solved a problem in complex number theory and everything else. And it's very useful in physics and a lot of parts of math. And it's able to handle orientations. You can see, especially if it has to be a unit quaternion to be able to do it. And it seemed like it was very convenient for that. And up until that point in the field of robotics and in computer graphics, pretty much like these 4x4 matrices were always used. And back in those days, we're talking like the early 80s, there was not really any specialized hardware to do this matrix multiplication. That you had to do it in software, which meant you had to do everything out serially one at a time. So it was very slow every time you did something like that. And we're also very, very memory conscious of being able to do it. So there had to be a better way. And I think it was around 83 or 84. There's a paper at SIGGRAPH showing quaternions versus 4x4 matrices and how they could be done and how fast they were. And a couple other properties is that the matrices we talked about last time are actually orthonormal, which is a very nice property. And an orthonormal matrix times another orthonormal matrix gives you an orthonormal matrix. The thing is, we're dealing with floating point numbers. And so we're going from like a theoretical world to an ideal world. And what happens with floating point round off is it can accumulate and either cause sometimes a row or column to get bigger than one in magnitude or get smaller. And that over time, this error can magnify and explode. So if you keep on rotating the same matrix again and again with different operations 1,000 times, suddenly the square or this cube that you're rotating starts to get distorted. It looks more like a trapezoid and have all these weird things. Whereas the quaternion has way more stability and it has fewer operations. So everyone just thought, this is the savior. This is what we should be using forward. It's just one problem with quaternions. Um, they're really bad at being it's really hard to transform a point. So the whole idea of these 4x4 matrices is that when you're all done, I've got an object that I now need to draw in some new location in space. I have to transform all the points that make up the triangles and polygons of that thing and have to do it quickly and efficiently. And quaternions are really slow at that. You actually had to take the conjugate of it and basically make a quaternion sandwich out of the point to be able to do it. And it's really inefficient. And just about every algorithm is like, well, take the quaternion and convert it into a 4x4 matrix and then do your work and come out of it. And you're like, well, wait a minute, why didn't I just do it in the first place? Because that extra work almost is much punishment as it was if you just went ahead and did it itself. So the main thing might be is that you save a little bit of what they call this renormalization of your orthonormal matrices, where every now and then you have a dirty flag. After I've done it 100 times, let's renormalize the thing because it could be going bad. So you don't do it every time because it's expensive, but you know it's going to accumulate. But that was a problem in the early 80s because everything was single precision. Now we're double precision. Now we have these NVIDIA chips where you can have like these feedbacks. In the early mid 80s, we were starting from Silicon Graphics to have that where we could start to use the hardware to do this, to be able to get it to come back. But still, a lot of people were kind of fans of quaternions, not realizing that they really weren't useful in robotics and in computer graphics. And so it kind of went out of favor, but not before it got adopted by at least one company. So what I want to show here is an example where I just have a generic robot or
You're
a
happy to
visual.
share.
Oh, yes. Oh, yes, I do need to share. Uh, okay, so there we go. So what we have here is we have an example of a generic robot that's at some generic location in space. And the idea of doing robot offline programming, this is the original sim to real, okay, is that you simulate what you want your robot to do, and then you want to post process in the language of the real robots. The real robot will move to that location. And so we'll look at the location here where I have some pretty nasty looking XYZ values here for the which basically represents the yaw pitch roll values. Okay. And I can post process it into any sort of different languages. So the language up here is you see the Yaskawa JBI format, and these values here are the same values that were in the robot up there, and they basically represent yaw pitch. Well, actually, roll pitch yaw because they put out the X first, the Y, and the Z, even though the order of operations is different. The same thing with FANUC you'll see over here is that it's the same numbers. So the red numbers are all the same. And in FANUC, they actually call it out as WPR. So you know that those values are yaw pitch roll. In the KUKA KRL, they call them ABC. And they actually kind of put them in the correct order that this is actually Z, rotation about Z, rotation about Y, rotation about X. So while the order looks different, effectively they're all doing it the same way. They're really doing it roll, pitch, yaw, even though they might be displaying as yaw, pitch, roll. And then there's this curious little example down here of ABB Rapid, where you'll see they actually have their target location out here represented as a quaternion. So we can see the quaternion values that are in there. And so why did they decide to go quaternion and not everyone else? Well, ABB's been around longer than a lot of other robot companies. They were the first company to have an all-electric robot in 1972. And their first robot language was something called ARLA, which stood for ASEA Robot Language, because that's what the A in ABC B stands for, ASEA. And it was a bit of an inside joke because the biggest dairy in Sweden is known as Arla. So you go to the supermarket, all the milk comes from Arla, and you can even see Arla in some other countries, even in the US every now and then, you'll see some dairy products with that label on there. So it was an inside joke, but it was an old school language. And by the late 80s, ABB said, oh, we need to have a more modern language. It'll be more Pascal like, that's got, basically structured type of programming. And they came up with the rapid language. And at that time, everyone was like, "Oh, quaternions are the future." So they said, we're gonna use quaternions." And that's the only reason why. It's because they were writing the hype cycle in the late '80s and said that that's the way to go. But then the dirty little secret was, it turned out that's how they store it that way, but internally, they have to convert everything into the 4 by 4 matrices to do useful work and then convert it back. Now, the one possible upside of quaternions, and in the early 80s, everyone was so worried about that extra floating point you had to put out there because it took up so much memory on your disk and everything. The main upside is you don't have that gimbal lock on that conversion going back and forth, because sometimes yaw pitch roll, when you get to 90 degrees pitch or minus 90 degrees pitch, the values that fall out of it may make it a little bit unstable. And so the quaternions, in theory, and we're going to see, don't have what they call the gimbal lock, but it doesn't mean there aren't some mathematical issues with that. And that's kind of what I want to just talk about briefly here, is that this is how you are able to convert a quaternion to a direction cosine matrix. And it's actually not too bad. I mean, you expect to see sines and cosines in there, but no, it's just a bunch of polynomials and stuff like that. So it's fairly straightforward to be able to then take a quaternion and turn it back into that. And now if you want to look at the math going the opposite direction, you say, well, then it probably isn't that bad if I have a 4 by 4 matrix, or the upper 3 by 3 and want to go backwards to a quaternion, what's that going to look like? Let's see. So if you remember, we get something like this. We're going with the yaw pitch roll. That makes it a lot of effort. Just, in comparison, you see that we have to solve this problem, lots of sines and cosines. So, but to go back, this is basically what the algorithm looks like. Okay. The algorithm is that you calculate these sums down the diagonal and you add 1 to it, and then you take like the square root of that number and divide by a half. Now, if you actually go through and look at this thing here, you can convince yourself that that trick works. That you go through it and you can actually isolate what your A, B, and C values are. And now this here on line 4, that's a sanity check, just to make sure, because you're dealing with floating point numbers, that you don't accidentally have something that's a little bit less than 0, because the square root function will misbehave and get really angry at you. So that's just to make sure that it doesn't blow up. In theory, you should never get a value less than 0, but that's theory. In practice, you always have to test against it. However, down here is where I get nervous. And that is, you'll see 15, 17, and 19, you have to make a decision on what the actual sign is, the SIGN is, of what is effectively your BCD terms. And it's based on this test. And it's a greater than, not a greater than an equal. And you might think that it's foolproof and doesn't work. And this is the problem, is you're working on the edges. So this works great in the middle of what's going on, but at some point your orientation might go to like 180 degrees or at 90 degrees or something like that, which is kind of like, it's not really an edge case, because people tend to orient their robots more perpendicular to objects than any other orientation, which means you explore this space more than you want to. And the result is you can end up picking the wrong sign direction of these things, which means the orientation is wrong. And this is something that we noticed at some customers we were downloading, and suddenly the orientations were flipping. And it's like, wait a minute, what's going on? And we ended up coming up with our own algorithm, and it turned out it was the same algorithm that ABB was doing. I found from a guy from ABB said, "Oh yeah, we have the same problem," and that is what you have to do is actually test all the different signs for B, C, and D to see which combination gives you the original matrix back. In other words, it's like checking your math when you solve the problem in algebra. Oh, plug it back in to make sure you get the right answer. You have to do this, except with matrices. And you don't, so you didn't know. So you went through, you would think you would try. And if it turned out your initial guess was right, well, you're done. And usually your initial guess would be right like 99% of the time, but we had to catch that other 1% where things were going bad. So that means quaternions, they're not quite as great as everyone thinks. And while they exist and some people are using it in some very narrow cases, everyone prefers using 4x4 matrices internally. You just represent it something else. Okay, so what's this got to do with the quaternion drives and that? Well, since we're going to talk about quaternions anyways, I figured I'd give everyone some sort of fundamental grounding on what's going on there. But the main takeaway with the quaternions is, of course, this idea that you've got something which is uh, uh, an axis that you point in space that you rotate about. And this is sort of what I was thinking. So, wait a minute, isn't that kind of what the hip joint is doing? Isn't the whole idea that maybe if you kind of point something in a certain direction and then just rotate about it, that would be an idea of how you could get a ball and socket joint to work. So this is where I came up with this crazy idea of what I call the quaternion drive and what this looks like. So I'm going to have to share my other screen right now to bring it back up and make sure I get the right one right here. Yep, that should be it. And now I just need to set this thing up. I think you should be seeing it right now, correct? And I'm going to come on over to here and I just need to make these things visible right now. And that is, let's go ahead and make the quaternion drive visible. All right. So now you should be able to see this. And the idea of this is, imagine I'm going to just go ahead and take this and then kind of break it apart. So imagine you have a cup down here, and here you've got a ball, which is typically how you would make a ball and socket. And then imagine you have a servo drive right up here, and that you take that servo driver actuator and you actually put it inside of the ball and the ball inside of the cup. Okay, so that's what we're going to do. We're going to go ahead and take these and kind of pop them back in there. And you can see in the backside down here in the South Pole, we would go ahead and this is where we run our cables and power and everything else that would need to go to that actuator to get that to work. So the way you can imagine is say, okay, what if I could somehow take this ball and then just be able to kind of move it this way and move it that way, point the axis in the direction I want, and then just go ahead and rotate this thing. I mean, so that would be sort of one way of solving the problem, right? So it's like a far hit, but being able to do it. So how would you do that? Well, don't know. So what you're imagining is that we know how to align magnets inside of a motor that we can get this thing to spin. I mean, that's exactly what this actuator was doing. Is there some way we could also align them around in there to convince this one? So, would you have maybe some permanent magnets in here and then some electrical magnets out around there that would allow you to orient and move this thing around? So that's assuming a certain amount of magic that does not exist yet that would allow you to point it in that direction and what's involved. Now, there are some problems here. One is that limited range of motion. So depending upon how big this actuator is up here, you see I'm kind of limiting how far I can move this thing back and forth without hitting. At the same time, I have to be careful if I'm letting this jet out, and I'm sure there's ways of getting around this that are more clever than what I'm doing, making sure that that doesn't hit the bottom of your structure because you need a lot of this to be able to get that to move. You just can't say, I'm going to have a thin strip and it's going to work. I don't think it quite works that way. The other thing, and this is the fly in the eye, if you want to look at it this way, because it does look a little bit like an eyeball along here, is that what happens when I am rotating this actuator? So when I spin this really, really hard, what's happening? It's creating a torque, right? Now, when it's spinning, it's creating, and if it's creating a torque in this direction, it's also creating a counter torque the other direction. So what I'm showing here, this is not realistic. And what we really need to show is that as I rotate this direction, that motor is gonna wanna go the other way, which means the eyeball is going to kind of go in the opposite direction. So it's like, "Oh, darn it." I mean, that's the thing about a ball and socket joint is that it's actually 3 rotations, 3 rotational axes you have to deal with. And this idea that I'm just kind of letting it go left, right, forward, backwards, and forgetting the fact that it's able to spin in there, I need something to be able to prevent that from spinning. And that means whatever I'm using to kind of control the position of that is also gonna have to be able to resist that torque at the same time of what you put in there. And then it kinda comes down and say, "Well, wait a minute, if you can design the thing to resist that torque, why not just use that in the first place?" Why go to even the bother putting in there if you can just go ahead and maybe be able to spin that eyeball in some way? And that would be really cool because then it wouldn't have any cables or anything else going in there because that whole thing would just be spinning around and everything would be coming into there. The thing is, I just don't think there's any way you can come up with any collection of magnets and anything. Hopefully, I'm wrong. Maybe there's some guy out there who really knows a lot about motor design. It's just impractical to be able to do that, and you probably would not be able to come up with that. As much as that would be my dream to see something like that, there's a lot of realities, to say nothing about the packing. So, for example, I tried printing out, an actual version of this, for today. Yeah, yeah,
Oh,
yeah,
okay. I was about to
and it
ask
took
that.
and it took me like 4 days just to get to here, and I decided that was, like, too much, and already we're seeing it's, like, it's bigger than a grapefruit, it's like, so we're talking because we needed something that would be able to accommodate the, whatever size actuator we have to be in there. Now, maybe they'd be able to minimize, but it's gonna be, and we're not even including the size of the cup. So then you start figuring out, well, is that gonna fit down there? It's like, well, your gluteus maximus is maybe about that size. So maybe it's not impractical. It's just that, there's probably wishful thinking. There's a lot of other issues that are going on there. And one other I kind of look at that may kind of say it's not necessarily the best idea, to do it this way, but we have one company out there that is saying, "We plan on doing ball and socket the next one." S That's P&D Botics. P&D Botics is planning on doing that, right? So, how could they possibly be doing it? And are there some things we can kinda learn from the design? Well, um, remember this mechanism here that we've seen in Optimus wrist and that we've also seen in iron from Xipeng? That is a parallel mechanism that's able to get like 2 rotations out here in the wrist. But remember, this whole thing rotates around here. So basically, it rotates first and then it does the business down here. And I was thinking, what if you turn this wrist around? What if rather than having the rotation of the wrist happening first, what if you had it last? Could you come up with a mechanism to do it? So once again, just to remind everyone what this mechanism looks like, um, as the 2 of them go together, you end up getting a pitching, and as they go in opposite directions, you're able to get the yaw, and you're able to get that to move around. So that's one way that it works. So let's see, is there is there some other way we could do it? And this is where we come to, what I think the quaternion drive is gonna look like. So I'm going to go ahead and share once again, uh, what everything is going to look like just to get us, an idea. So think I am sharing this, probably not sharing the screen yet. We will go ahead and here, and I'm going to be there. And now I need to also do a little bit of a setup. We're going to go ahead and show like the first way of doing this, which is going to be this one here. Okay, so I think we can see that. So imagine we tried building a hip like this. So right here, this is your spine coming on down there, and we can see that we have, your femur up here, and then your lower leg joint down here. So not the greatest graphics or CAD, but it's basically to get the idea of what's going on. And so here's that motor that I was thinking of putting inside the ball. So again, the same idea is we get an actuator here, and what we want to be able to do is point that actuator in any direction. So what if we take that mechanism here and start thinking about doing that? So what you would do is you would just go back and forth like that, and this will give you abduction. There's your abduction. Okay. Now then, we have the other way that we can go, and that is like back and forth like this, and that gives you your rotation. So that's two possible ways of being able to get this to work. Now, you have to be very careful. Is like if we look at this, I probably have to make that ring a little bit better, design it because you see, if I go too far, I get a little bit of collision going on here.
Yeah.
So these things are constantly going to get into conflict. And you also have to be careful is that if you look at these joints, now these are spherical joints, also known as Heim joints. They don't work really well in that yaw direction. Okay, so that back and forth here, they only can go so far before they also begin to interfere with each other. As far as the pitching direction, there is no problem. They can rotate almost ad infinitum in there. It's only this problem here. the the fact that you get the self intersection kind of going on. But their range of motion is really pretty good. It's the restrictions you're having are others. The main problem with these is that you only have a limited range this far before there's a problem. And of course, you need two of them. You have them back here as well, kind of going back and forth, as we can see, on and on. So if I'm going to remember, yep, this one going back and forth. So you see, we can get almost what we wanted to do with the idea of a quaternion drive, of being able to get this axis out here. Now, why would we go ahead and do this? Why not just do it the old-fashioned way of stacking the actuators together? And this has come down to that whole argument. It's like, well, we don't want this actuator, which is the flexure, to have to carry the load of
Mm.
the abductor and also the rotation. We'd like it to somehow be last in there. By putting this thing up here, we don't have to worry about carrying that. That's right in there. And we get that 2 for 1, the idea that, well, the abduction is the one that's really the most important one. And we can get twice the power out of these things here. And when necessary, we have enough for it. So that means there's a lot of upsides to this kind of idea that could be attractive. Now, the packaging is probably way more difficult than I'm looking at. I think I'm unrealistic on the lengths of some of these things. They'd have to be a little bit longer in order to make sure we don't have these conflicts of everything kind of bumping into each other. We are going to have to do things definitely a little bit differently than what we see here. But again, I think that's more or less, just kind of good CAD design, figuring out that's in there. The main thing is like, is this idea worthwhile exploring or not? And is this something that P&D might be looking at? I don't know. This is my I'm trying to rack my
Quick
brain about
question.
how they would do something like that.
Quick question. If they
Sure.
turn it out, they did exactly what we said in this episode. Do you think so?
I don't know, and part of the reason is that they haven't shown any predilection to using linear drives anywhere in their bots. So I think they may be focused on rotary, in which case they may be coming up with another rotary because there are some other schemes that we'll kind of look at that you could use for something like that. I'm not
Mm.
sure if they're going down that route or not. And my actuation strategy is like this very futuristic, the ideal way of doing it. There are a lot of people that have tried to actuate ball and sockets, but they're very cumbersome with, basically gears and stuff like that in very strange shapes. I think people have seen those on YouTube. The problem is they're not very fast. They can't produce a whole lot of torque. The positioning accuracy is horrible. There's like all sorts of reasons you don't want to do it. But this is one potential way of doing something that is like it. Now, I don't think I would call this a ball and socket. Um, because a ball and socket is really a ball and a socket. This is a cylinder that's being carried in a cage. Okay, that's a little bit different. But it's attempting to do the same thing, just through different means that could be of interest. Now, maybe this is something that Heptronic would consider or Xpeng would consider because they're doing a strategy like this, except they're putting these things in the leg itself. So they have the rotary first, and then they have the flexure and the abductor this way. So maybe they would think about something like this since they're inclined to it. But my concern is whether the offsets become so long that your legs are like really far apart. How do you package them? I'm sure there's some clever design engineers that would figure out a way of being able to do it just by changing a few angles, maybe going past the center. And, because right now I'm saying, oh, it can't go past the center. But realistically, there's probably no reason why it couldn't. Uh, anyway, that's one approach, but there are definitely other issues that we have to kind of consider going on with that. And that is, like I said, the range of motion is horrible in what would be like the rotation with those joints. So we get limited range, maybe plus or minus 30 if we're lucky, and that may or may not be enough for the rotation of the leg, depending upon how you actually want them to work. And there's another thing that while going through some old posts, I noticed this one from Cornelius Ong, where he kind of talked about one of the problems with spherical actual or just say spherical joints. And that is the backlash they have in there. And this was in a different context, the context just regarding about waste using something like this, where you have again that spherical Heim joint in there. And that, I've mentioned before, they are kind of sloppy. And this case, he's saying, yeah, I mean, they could be pretty sloppy in your torso. That if you're, and that could result in you losing like up to an inch of wobble at the head and your shoulder, which could make your positioning accuracy pretty bad, depending upon how critical that is. But they're not necessarily the best solution for being able to get the movement that you want because of slop. And also, we saw that there is that minimum range of motion. Okay, so that kind of pertains to what we've seen with the Tesla wrist and also the iron wrist. Um, and now there's two other wrists that use the same kind of strategy. This one here actually comes from Medea, which you may know as the world's largest appliance manufacturer of dishwashers and microwaves and other things in China. And also here is the Aptronic Apollo. So they're using the same actuation strategy, but you'll see they don't actually have a Heim joint here. They've got something different there. And that actually allows them to have a much greater range of motion. So let's take this idea and see if we can incorporate that in and make a modification to it. So that's what we're going to do now is we're going to go ahead and see about looking at the next instance here. And I will go ahead and bring up the other one for contrast back here. So we can see what I've done now is that with this, I have way greater range of motion. So it's the same in this direction. That's not really going to change. But when you decide to go this way,
Oh, yeah.
you can really go. Now, the problem is the conflicts that are happening elsewhere, the fact that my actuator is too big and everything else. But as far as this goes, and even in here, you see, there's a problem there now, but that could be done with a different separation distance. So it allows you to get a much greater range of motion.
So what they actually did, remove the ball stuck.
Basically, you don't have the ball there anymore. And what you do is you are using a pin joint right here. So
Mm.
pretty much you have a rotation along this axis here, that pin there. So you actually have 3 rotations. You also have a rotation along the shaft that you may not notice. You might think that this is actually welded in the shaft. It turns out this piece here actually has to rotate, or the whole shaft itself, but I suspect the shaft doesn't like to rotate. So you have to have a pin joint here, a pin joint here, and a pin. So basically you're going 3 joints. So you're taking that one spherical joint and turning it into 3. And probably in combination, they're just as sloppy as the spherical joint. Okay. I don't, and the stiffness there doesn't look that great. However, it does improve your range of motion considerably. Now, what you might be saying, yeah, but you may have solved the problem there, but you still have these Heim joints back there. You're not going to be able to solve that problem. Well, actually, the ones back here, they don't really care. They don't move that much. So if we actually look at how much it moves, most of the movement is up and down, but not as much as we're used to seeing out here. And then as far as like the back and forth, there's barely anything going on here. So you can go ahead, and that's exactly what Aptronic and Xpeng has done with theirs. Is they have a Heim joint back at this part here, but they have something else because it gives them that wider range of motion that they'd want to have on the wrist. So that's one possible solution. And then we can go ahead and sort of see what these things look like in action. If you're to have them moving around, something like that is that you can get the flexion, you can get the rotation, and you can get the abduction, adduction. Maybe enough. I'm assuming this would give you the range of motion you want. In some cases, may not, depending on how much abduction you think is needed. If you need more than 90 degrees.
Scott, this is because they use it in the hand, but did you see anyone use this in the leg?
No,
Like some
no,
no.
no,
Okay.
no one's done anything like that. So this is just kind of turning around as another. Now the advantage here is that you may not have noticed, but I'm kind of suggesting that there could be an actuator in here, because this is the flexure actuator right here, which is making the leg rotate. There could be another actuator built in here, which is the one that makes the knee move. And what you've now done is you've taken all your actuator mass and you've concentrated it up here. You're getting it away from the leg having to carry half this mass. So that's the only advantage of doing this, is that you might lighten everything up. That just means your torques go down and the advantages of things. But it's going to come with a potential loss of range of motion from what you want. Now, if it's not supposed to be a gymnastics robot, but it's being used, basically be able to at least walk like we do and squat and do a few other things, it may have sufficient range of motion. But beyond that, it's not gonna be super, super flexible. That's definitely gonna be an issue. So, that's the idea. Now, as I started exploring this a bit further, is that, what kind of, hip do you think this is? I mean, if you were to
Mhm.
classify it, because remember we talked about a far hip and a RAF hip and everything else.
It's
If you
ARF. It's ARF.
Yes, yes, definitely is ARF. So the abduction kinda came first, and then there was, like, that rotation, and then flexion is last. So flexion is at the very end
Yeah.
after we've done all those other things. Now, is there any downsides to that? 'Cause,
Yeah.
order of operation matters a little bit, but is that really at the end of the day, is that gonna affect how we're able to do things?
Yeah.
Um, and before I kinda go on that, I just wanted to finish up is that there are some examples of, I guess you'd call like a spherical actuator. You may have seen that there's actually a bot, if you remember like BB-8 from Star Wars was on a
Mm.
sphere and like moved around that way. And there's actually people that have recreated bots doing that, and examples of, whoops, let me get back to there, is using these wheels. And if anyone remembers the old school mouse, I'm talking like probably pre
Yes.
2000, because the mouse right now is an optical mouse. They actually had a ball in it, and the ball would move around, and there were actually like little wheels inside there, 90 degrees to each other, that would measure the rotation in one direction or the other.
Mhm.
So that was being used as a way to measure the movement rolling of the ball versus actuating. And you could imagine, well, what if we turn that wheel around? It's like, well, you can kind of do that, but you got to remember it's easy to actuate in one direction, but when you do another, there's going to be a lot of slipping along that wheel, skidding, and it's like it
Mhm.
just it's kind of crazy and it's really challenging. You see, this one here is rather interesting. They're using just three wheels that are like 120 degrees apart, which I guess in theory you might be able to get every rotation, but I think there's some directions where the torque won't be as good as in others.
Is
So
it the
I'm not sure.
grasping? Is it for grasping or what?
I think this was like the example of this was just proving it could balance on a ball. So
Mhm.
this was like a research project. Just say, let's put it on here and see if we don't fall over. So, the super challenging inverted pendulum problem. This here may have been another one where it looks like, something out of Back to the Future that Doc Brown put on his head. But this, I'm not exactly sure how this works. It may be that it has like lots of wheels that are along here all the way around there to give a lot more control and movement. So if you were to build a real ball and socket, it might look something kind of like that. And the question is that overly complex? And would it kind of fit the bill? So maybe this is closer. If these are actually wheels that are moving, that seems like what you've done is you're adding a lot of actuators, or maybe not. Maybe they're all kind of tied together to a single actuator and using some sort of chain belt or something like that to get them to move. But, it could be a very complicated mechanism, but that might be one approach that they're taking. Maybe they've found some way to be able to scale it down. So that's another possibility, that through mechanical means of doing it. The ones that are out there, no one is convinced that they can deliver the torque and acceleration, everything else, positioning accuracy that's demanded by the robots. But I'm glad to see someone is thinking of trying it anyways to see what the results are gonna be. Okay, so, yeah, so that's what, P&D is gonna try to do, something like that, get a real Paul and socket. I can't wait for that. Um, and
You know what?
again,
You
mhm,
know when
mhm.
they release it?
I don't know, they're working on their next generation, it must be that they've already got it at least on the drawing board and advanced enough that someone from the company is willing to make that statement.
Oh.
And hopefully, since I was like maybe one of the first ones to hear about that, will be the first ones to see it. So I'm trying my best to learn more. Now, if we remember, these were some of the different hip configurations that we saw. And the FAR is that you do the flexion first, articulation, abduction, and then rotation is the very last one down the leg. And then the other strategy is to go ahead to the AI, to the ARF, which is what they do in the Tesla bot, in which, in theory, our little quaternion drive is doing as well, where
Mm.
flexion comes last. And is there any consequence to that? And it's hard to say because remember the original one, everyone was ARF, and then everyone moved away from ARF and went over to FAR, and only Tesla is there. And are there any conclusions we can come? And one conclusion, I think, after thinking about it more, is that for now, I found a second reason that Optimus will suck at soccer. The first one is that because it didn't have the head movement back and forth, it will not be able to do headers the way Ronaldo is able to. But it also turns out, more importantly, it won't be able to kick the soccer ball correctly. Okay,
Mm.
so let's go down that rabbit hole. You may have seen this post about a week or so ago. That comes from Booster Robotics about a soccer playing bot, and it was rather interesting to look at this. And we'll just go ahead and look at the full video, and you can see what's going on. And sure enough, these bots are competent at being able to kick the ball. But
Mm.
do you notice anything about the soccer skills? Does it remind you of anything?
And the leg, I think I saw this robot at Iris the last year.
Hmm. Hmm.
The leg has this kind of mechanism in the near the foot. It's just yeah
It's
different.
it's just it's basically it's a variation on a theme of using a similar
Mm.
kind of way of being able to move it. But the thing about it, if you look at this, this looks like kiddie soccer. Okay, it's like it's not much more advanced than kiddie soccer. They're pretty good at
Alright.
kicking the ball and everything else. But what I want to do is look at this clip right here. This is very important.
Mm.
Now,
Oh wow. Yeah.
look at the robot and look at the human. Look at Can you see how the human is kicking the ball
Yes.
and how the robot is kicking the ball,
If
okay?
it's straight, like the robot straight angle a little bit.
Yes, okay? So, the human is basically kicking it the proper way. Maybe it's not, the perfect form, but it's what you're supposed to do.
Mm.
You're supposed to kick the ball with the side of your foot. So, you notice how his foot is turned, how his knee is pointing out when he comes in to kick the ball, and you notice they kick it toe on.
Mm.
You're not supposed to kick it toe on, unless you're trying to kick field goals or something like that, and even field goal kickers now are sidewinders. So, you don't wanna kick it that way, and at first I was thinking, "Oh, is there something wrong with the design of the bot?" So the first thing I said, "Let's look at the hip. Is there something wrong with the hip design that's different? Did they take something out?" What kinda hip do you think this is?
Oh, this is definitely far.
Yep, yep, yep. So we can see, the red axis going through here. We can see the blue, and we can see the green, and so we can see that rotation. And so it kind of mystified me. Says, the thing is, they're just not teaching the bot correctly. They know how to kick the ball. I mean,
Yeah.
I don't think that was necessarily like a soccer trainer out there. It's probably like one of the guys in the booster team, but he's played soccer in his life.
Mhm.
And he knows how to kick the ball. It's like, okay, come on, show them how to kick it right. So that comes up the big question, like, aha, what are they doing wrong? And is there something about these mechanisms that makes it difficult? And now we're we're going to now compare this with Optimus. And that you see, Optimus is different. Optimus does the flexion last,
Yeah.
and it does the rotation basically in the middle before you get to the flexion. And this is going to be very important on why it's going to have difficulty, whereas the robotics can do it correctly. So the first thing I want to do right here, this is just a reminder for me to say, I want everyone to pause and look down at their foot right now. And I want to take your foot and I want you to rotate your foot so that it's pointing, say, 45 degrees to one side. Okay.
Mhm.
Now look down there and ask yourself, what did you do to rotate your foot? How did you get your foot over there?
From the knee. I think the knee, more than the knee.
Now think about it. Look at it. Now, you could have taken your foot and just rotated your foot that way, right?
I'm not
And if you
standing, so
if you did, you're a very special person because almost no one can rotate their foot that way. You can make your foot go up and down like this, and you can roll your foot, but this idea of being able to just rotate your foot by itself doesn't happen that way. Now, you might think you rotated it below your knee, No,
Mhm.
you're not rotating it below your knee, because if you did, you're talking ACL, PCL, and MCL tears, okay? You are not doing it that way, and in fact, if you look at all the humanoid bots out there, you'll notice their ankle only has 2 degrees of freedom, it doesn't have 3, and there is nothing below the knee. The knee goes back and forth like that way. When you actually look at it, y all that rotation is coming up here from the hip. Your
Ah,
knee is pointed in the same direction as your foot. If you're rotating below your knee and your foot would be rotating differently, but they are basically in the same direction. Now, that means in order for your foot to point in that direction, you only need rotation up here, which is why all the hips need that rotation. It's very, very important. And you need that rotation to turn when you're walking. Without it, you're going to pitter patter your way over. But if you turn it over like this when you do your plant, it's a lot easier for you then to get your body around to continue on. So that means they have rotation. That booster robot has rotation. They can turn their foot, they can get it in that direction. But what happens after you get your foot into into this position? What do you have to do to kick it?
now you have to flexion, deflection.
You have to swing forward like that.
Yeah,
You need the flexion to come through.
yeah.
And they have the flexion joint as the first joint, which means when they get their foot in that
Okay.
orientation,
Mm.
they come through like that. Now, guess what happens with Optimus?
Yeah.
In order for Optimus to do the same thing, if you want to get your foot to the side, Optimus rotates over this way. But
Mhm.
guess which direction is its flexion? Its flexion is in the direction of the knee. It's in the
Yeah.
same direction as the foot. Now, okay, now you let's see if you can do that. So, if you take your foot and turn it, everyone take your foot, turn it, and try swinging it forward, and you see you can do that fairly easily, okay?
I
Now,
don't yeah.
the kicking it in the direction of your foot, surprisingly, you can do it, but it's hard and not with a whole lot of power. And now you might do something like that for some tricky soccer pass or something like that. And if you probably do a lot of exercise, you can strengthen your abductors enough to get that. But for the average person, they don't, it's a very difficult maneuver to be able to do that. Now, maybe that will be a cool soccer trick to fool the goalie that you put your foot out there. He thinks you're going to kick and like you power kick it on that way. So that would be one advantage. But assuming you need to come through here, will Optimus be able to do that kick? And that's what I want to take a look at right now is we're going to go to our old friends that we have here, and that is the decibel. Okay, so I think you can see that now, right?
Yeah.
Okay. And basically, I made two types of legs here. So over here, the right leg, which is on your left side right now, is a far actuator. Okay. So what we have here is like, let me get that thing back there. So this here is the abduction, and let me get that there. Okay, so there's the flexion, there's the abduction, and there's the roll. Okay, going back and forth like that. And then if we look at this one here, what we're going to see is that we have the abduction. Oh, sorry, that's the roll. Let me get there's the abduction, then there's the roll, and then there's the flexion. And the flexion is down low because that's where Optimus has it. It has it well below there. Okay, let's imagine I want to kick the ball the proper way. Well, with my right foot, I'm just going to go ahead and rotate this. Let's say, about like that. And then I'm going to come over here and not moving the hand. Let me get the right. And you see, I can kick all day back and forth, back and forth, back. That's really easy. I just move the flexion back and forth and I can kick it with the side of my foot very easily. That's not a problem. Okay. Now, let's see what happens when we try to do it here with Optimus. Okay. We move our foot over like this, like we would want. And now I want to kick it. And I have to do it with my flexure. You see, it's kind of kicking in that direction. Okay. How can I get the foot to actually kick forward? Because by doing that, I'm kicking with my toe. The idea is I want to kick it with the side of my foot. So what I would need to do is that as I go forward, I need to kind of come in a little bit with abduction. Go a little bit more forward, up, a little bit more abduction, a little bit more forward, a little bit more abduction. So you see what we have to do is we have to do both at the same time. And as you see, the further I try to get my kick up there, whoa, wait a minute, that doesn't look good. What's going on here? And it's like, whoa, wait a minute. So you'll see that this is causing a little bit of a problem in the ability to do something like that. Now, are there further ramifications to being able to do this? And I'm thinking there may actually be, because when you're walking and you want to turn, so I'm taking a stride and I have my leg kind of out like that, and I want to twist it a little bit like this, right? And then get ready to put my foot down. So I need to get that rotation, but I want to be able to keep my stride going forward. So I want that going forward before I plant it, because by turning my foot, it will allow me to turn my whole body when I put it down. That's going to be trickier for Optimus because it gets itself kind of up there and it wants to get its foot off in some other weird direction like that. And it really wants the flexion to be more forward and not off to the side. So that means when Optimus really starts doing its turns, especially if it does a rapid turn, it's going to be weird. It's going to be a silly walk, no doubt about it, because it's not emulating the way we walk ourselves. It's just the the way they've designed the mechanics will kind of prevent it from being able to do that. So I think you'll see it's just got this very strange walking behavior when it decides to go around corners. That's one of my kind of takeaways. Again, that architecture is going to potentially cause some problems. And so right, and so then it comes back to the quaternion drive, is that the quaternion drive is ARF. And so it's like, oh, you come up with that whole thing, and now you're kinda moving like that, and you might realize that, oh, it's gonna actually take away some
Oh,
capabilities.
wait, can I ask a question?
Mhm.
Because in the Optimus, you say they have this limitation when they have to make the movement like soccer. Do you think if they have to the waist design to make enough space for the movement to happen?
They
That's
they
my
m
concern.
they they might be able to if they make everything concentric. So I think the real problem they have is that their flexure is below where the rotation and the abduction intersect. So they're not concentric, and that's what they need to be. And so I've got a slide on that, which I think will help remind us of exactly how it's set up. So it's basically this: if this red was up there, I don't think we have a problem. So maybe the quaternion drive idea wouldn't be that bad because it's sort of happening up here where you won't get that problem, and you're trying to rotate it around. So maybe it's not that bad, but still, dropping it down here does complicate it, and again, makes it very difficult. So you can't take your most powerful actuator and actually get it to stay in what is the flexion plane. I mean, that's actually, the biomechanics designed to find that plane to be right there. That plane's not supposed to rotate. But what the robots are doing is they're rotating it and now trying to do the flexion that way. And it's like, no, 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 that's not what you're supposed to do. Flexion is supposed to be in the flexion plane. And now you're taking it out of plane and trying to do that. So your movements are definitely going to be different compared to if we go um, to the normal kind of actuation strategy you have here. Not only is flexion first, but everything is concentric up here, which is the other advantage of that. So those will be some of the things that'll be interesting to watch out for as if we start seeing Optimus more and more in public, exactly what it's going to be like when it starts walking more like us. But right now, we haven't really seen it walk that much like us. We've seen it come out pretty much marked mostly in a straight line. It's done kind of some slow figure eights. Haven't had an opportunity to really examine that, but it'll be interesting to see when it's walking at normal speed and trying to cut a corner, whether it has a rather interesting movement in its hip to be able to accommodate for that. It's probably have to come up with a completely different strategy. So it may be that I'm too human centric on thinking about how we walk because we have a certain kind of mechanics. And it might be that it's able to do it kind of fine. It's just going to be a little bit different than what we're expecting.
I think it's very, very, very interesting. Every episode, I think I'm learning every time. I think audiences learn. It's super fun. It's just really fun and enjoyable. And I just want to say, do you plan to patent this quaternion drive?
I don't know. I mean, I kind of wonder if there's anything patentable there, but
I wouldn't give up in it, to be
Uh,
honest. Yeah.
there may be some approaches of doing something like that, that may have some value, but again, I'm a little concerned about the range of motion, but those are things that probably could be cleaned up by having a better mechanical designs, 'cause it's a very rough design that's there. As you begin to see where all the interferences are happening, you can probably design around a little bit, and like I say, there are ways of increasing the range of motion on the where we had that Heim joint before. It's like, okay, you can come around there. We've already seen others have kind of solved that. Um, and again, it might just come down to that how much range of motion that you have in there. But again, let's go back to remember is like, this is what we've got in our hip anyway. We have this, and we can maybe increase, and what limits the range of motion is sort of the diameter of the neck of this up here. If that's too big, I won't be able to really move around very much. And of course, the size of the cup. And, the size of that is just wanting to make sure that that stays in there nice and tight, but you could probably also make it a little bit better. It's just coming up with the actuation strategy, but we know a ball and socket joint has the range of motion that we want because we have one. We don't need to have more than 180 degrees this way. Probably 135 is sufficient and 135 is sufficient that way. Maybe even less, maybe 120 is more than enough. And all we need is to have like, I mean, in theory, mine would have like infinite in this direction because you just rotate. We can't do that with our leg. Okay. You can do the splits, but for the most part, we aren't more than about 180 degrees in the movement of any of our joints. You go beyond that, and yeah, you're like, you're super flexible or you're risking injury. So, um, there's nothing wrong with designing something that might have constraints like that in there. And maybe there is some clever actuation strategy that will allow you to get that range that you want, but it has to be compact. I mean, the whole idea of you coming up with this is to try to come up with something which is compact. And if it ends up being much bigger, much heavier, more complex, and more costly, you have not saved yourself anything. So it's kind of an intellectual exercise right now. It's like, oh, how would we do it? What would be different ways? And there's nothing wrong with that because the first ones will come out and they'll just be absolute kludges. You'll just look at it and it's like, oh my God, what a mess. I mean, it's too complicated. But eventually you'll figure out how to improve and improve and improve. And then at some point, someone might be able to come up with one that's reasonably compact and has everything you want. So you got to start somewhere. Your original designs are going to be horrible. I mean, it's like I'm already starting in mine and realizing right away, it's like, don't even bother printing the whole thing. Make a nice little salad bowl or something right now. I don't know.
No, I'm sure you will finish it up.
Yeah.
It was a really great episode. The first part's a bit heavy.
Yeah. 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 Hopefully, I mean, I was afraid of getting too far down that rabbit hole, but I think I want everyone to sort of know what quaternions are. Look it up in Wikipedia, read about it. Actually, go to ChatGPT and ask questions about it because Chat was able to help me make sure I get some of my math right. Some things that I'd kind of forgotten about on how they work. And you'll begin to realize that like why quaternions were kind of a fad for a while, but they ended up not being useful. It doesn't mean people who are using it in physics and stuff like that, they're very useful. I mean, there are applications, something like that. But the application in robotics and the application in computer graphics, I have not seen that there's any advantage to it, especially now that we have these NVIDIA chips that can do a matrix multiplication just as fast as you can multiply a scalar together. Because bam, they're just designed for that. Everything is parallelized, so you don't have to worry about it. And in the end, it's the most convenient format to work with. Um, because today memory is not a problem and speed's not a problem.
So in initial, it's not that relevant anymore, the quaternion. I know what you mean.
I mean, for people in pure math, it's relevant. For people who are physicists, for people who are robotics, it's like one of those things you don't even have to teach it in a robotics course because you're better off learning the matrix math, like I talk, and I say you expand it with one more. Usually they call it a 4 by 4. Really, it's a 4 by 3. The fourth column is 0001, and it's kind of there for historic reasons and comes more from a CGI because you can bury some scaling factors in there for perspective divides and stuff like that. For the most part, that last column is always the same. You don't worry about it. Um, and uh, and so your hardware would be designed to just do it as a 4 by 3. So it's not 16 values you really need. It's just 12.
because all of that's very relevant for game development and video games.
Yeah, 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 video games. Yeah, yeah,
And you have been
everyone's
there,
using
I
it.
think.
Mhm.
I'm just curious, for CGI, what software do you use for CGI?
Oh, I mean, a lot of people, yes, we can output to, like, the Blender, and we can also
Blender,
output
yeah,
the
okay.
to, we have the format that will go straight into Maya if you wanna use that.
Maya, yes.
So,
Okay.
a lot of people like and they have the channels where basically the channels are yaw, pitch, roll. So you get, like, an XYZ offset and yaw, pitch, roll, and they control those things. The thing is, those things, you just can't use them on a slider bar and move those things around and get the kind of movement that you want. So this is a danger a lot of people have done. They said, "Oh, I have a starting yaw pitch roll value that I want my hand to be in, and I have an ending yaw pitch roll value that I want my hand to be. All I'm going to do is linear interpolate between the starting and the end, like I would with XYZ. So you can do that linearly with a vector, and they'll do that thinking they can get away with it. And yeah, you get like an interpolation, but you get this weird interpolation, which is not what you expect. It's not the shortest direction, and sometimes you can end up with your head like you may have seen that there was a FIFA, I don't know, 2010 version or something like that, where they had guys going up doing a header, and as they went to do the header, suddenly their head like twisted around themselves and came through their body and popped back up because the yaw pitch roll values were interpolating between like, minus 179 to positive 179. You're like, well, wait a minute, the shortest distance is like 2 degrees. Why are you going like way around the clock that way when there's a better way? Because the yaw pitch roll values, they don't see that in there. And that was like a really lazy, dumb way to do it. The way you have to come back, and actually the proper way in in robotics is you use single axis interpolation because single axis interpolation is actually the shortest move in orientation space to go from one orientation to another. Doing it through yaw pitch roll, that way you're going to take a long way to get there. So if you're wondering what's the shortest way to go there, that's one that's commonly used. There's another known as two axis interpolation, which is used for circular interpolation because sometimes a one axis interpolation gives you a result you don't quite want as well. That, but you have to break it down into these different kind of compound rotations that get you from one to another to make sure you smoothly interpolate to get the movement that you want. And yeah, usually one axis is something everyone should understand. That's critical. And again, quaternions will come up in the discussion. It's rather interesting because, like I say, conceptually, it's the same idea as single axis interpolation, and there's a very easy mapping to go back between the two. But one of them you can look at it and understand it. And the quaternion values, you look at it and you're scratching your head. It's like, oh, what's that A value? What's the angle of that? And it's like, oh, I'm going to take the arc cosine multiplied by two. All right, that's what the value is.
And what they use now for video games? Do you have an idea? Up to date?
Oh, I think I think everything. I mean, internally, everything is being done by these 4x4 matrices. The thing is, when they go to interpolate from one value to another, you do need to use a proper interpolation mode to get there. Otherwise, if you take like one set of matrix values, another set of matrix values, and you take each one of them and you just interpolate them from one to another, you're going to have something really weird. Your matrices will no longer be orthonormal. They'll start orthonormal, they'll end up orthonormal, and they'll take a journey through who knows where. And it's just going to be bizarro, and everything's going to rotate around, scale and stretch, and then kind of suddenly come back in. So you have to actually break it down and mathematically approach the problem by saying, how do I get from this orientation to that one? What's the axis that gets me there? And now just rotate to there, and now I'll get a very smooth interpolation. So it depends on how they do the rigging and all these things, the kinematics for them. That's in many cases in the early days, they got away with it because they'd move the camera so quickly, you couldn't catch the flaws that were going on. Because I remember seeing a lot of them that you would have these jointed models that were they actually didn't understand the tree relationship. Everything was in world coordinates. So they would have, their arms and everything in the world coordinates, and everything would come together at the next interpolated frame, which is usually what they call a keyframe. And then when they try to go between the keyframes, the whole body would kind of fall apart and then come back together again and fall apart and come back together. And the only way you could get it to stay together is your keyframes had to be closer and closer together. Now,
Interesting.
sometimes you get away with it if the rotation just happens to be a line along like your X, Y, or Z. But if the orientation you need is like a compound rotation, things go whoop, and then come back together like these big rubber band things. And so what they would do, and a lot of times it was slight, but if you look at it really closely, you would notice it. So the thing is that while they were animating it, the camera was like flying around really quickly, and you couldn't pick up on those little details of how it was falling
It's
apart.
really interesting. I used to, when I was young, to play BS, I think PlayStations,
Mhm.
and And now you're telling me these things, it just
Mhm.
remind me of all those
Oh, it was
crazy
it was
thing. I'm not playing anymore, but
the oh, yeah.
years that I would love to see how it looks
Yes.
like now. But you're right, it
You
was
took
like
shortcuts there was lots and lots of shortcuts going on how to get that to work right. And again, it's because they weren't rigging them correctly. They didn't have a full kinematic structures. Like if you have like the whole kinematic structure in that tree that you're going down each time, it just works. We never had that problem. And then we saw these animators and like, what do you guys I don't understand, you know? And then we realized, like, oh, we were making a big assumption. We thought you were also using a tree to describe the kinematic structure. And now it turns out they're just a bunch of objects floating in space that just coincidentally happen to be matching up the way that you want. And that was like, that's not a way to do complex kinematic
I
structures.
think in the episode we did the virtual reality, the kinematics, you remember
Yeah.
that? So I think you did it. There's were strange things in the model happening in the heads
Yeah.
movement, and maybe
Yep.
this is the same thing you're talking about here.
Yes, yeah, they could be, yeah, some of them were part of it, I think, was because I was getting reflections off my walls and getting bad data, which was then causing something to say, "Oh, you've gotta rotate way more than you're supposed to." So, yeah, so sometimes if you're getting that bad data, but they should not have things should not have been falling apart. Something like was turning itself inside out. I think it was because we were getting, like, some bad data that was saying, "Oh, I think the elbow is over here now. Oops, now I think it's there."
It's really, really interesting. I think did you develop any video games in the age?
No, I never did, and I
Okay,
never
but anyhow, the visual component software.
It's a video game. I mean, as far as I'm concerned, it's a video game for engineers. It's basically, a lot of the ways I describe it, it's like, well, we were kinda like Minecraft for engineers. You build a world, which is a factory with all these different things, and you can give them a lot of behaviors. You can program in the motions and so that's stuff that we were doing. So the similarities is it's like a video game. So I don't need to play them, and I don't need to because I'm already basic. And the thing is, we've a lot of our developers, either not only the gamers, they have gone to gaming conventions and developers conferences for that reason, because out of the gaming community came a lot of insight on how to improve some of the stuff for visualization purposes, how to accelerate some of these, lighting models and doing occlusion and everything else. So, and at the same time, the gamers push the technology. We wouldn't have the NVIDIA cards today. We would at least not at the price. If we had something even similar to it, it would probably cost still $100,000 because the only people needing it would be like big companies, you know. But if you want your average person to be able to have it, the price has to come down. And a lot of it came because there were so many gamers and enthusiasts. So we've definitely benefited from it. We wouldn't be able to do half of what we're doing without that hardware. None of that hardware directly comes from a response to the gaming community, the requirements of the gaming community, which at the time, people who were engineers said, "Oh, what dumb requirement. We don't need that." Only for them to be using it now. It's like, "Oh, these texture maps, yeah, they can come in pretty useful." Whereas the gamers were using it because they wanted more realism. And then like, "Oh, this physics stuff," it's like they felt like they didn't need it. It's like, "Oh, we don't really need it to do a lot of the stuff that was going on." The gamers are like, "Well, we want physics, in our games." And then you end up getting the physics engine and all this. So, yeah, a lot of what you're seeing that we're benefiting now in robotic simulation has come from the fact that the gaming community has very different requirements than us. And we don't realize that we have those requirements. We just think we don't.
I think you have the model, the electronic STL model, and you said
Yeah.
maybe we can use it for one episode, virtual
Yes.
reality.
Yes. Yes.
I
Yes.
think it
If
would
we
be
get
fun. And also, if we can expand more into because I think I really love this topic. So it's just super fun, especially the physics simulation. It's just and video games. So I think if we can do something, of course you prepared that stuff, and I'm just here to listen from you. So that would be terrific.
Mhm. Yeah. 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 I don't haven't quite figured out what next episode's going to be on, but um I wasn't quite sure what this week was going to be anyways, and things kind of fell into place. So it's usually there's something that kind of comes up that would be worth analysis and looking at.
So should we call this episode Quaternion Drive or
I
video?
think we'll just call it Quaternion Drive. Yeah, why
Okay.
not? Just go ahead and call it the Quaternion Drive, and then hopefully that gets a lot of interest. Exactly what is and this harebrained idea of mine. Uh, I have a feeling there's probably someone out there who's going to look at it and say, "That's not crazy. I know exactly how to implement this."
But again, thank you so much for the time, the preparation, and yeah, it's just I appreciate your effort. and the passion to live there. And I hope it will continue like that for
Well,
many time.
it's a lot of fun too, so,
Yes,
when you're passionate about something, it's never work.
it's contagious. I can feel I'm learning. It's blessing to learn it from you. Yeah, and the elders as well. So thank you, Scott.
You're welcome.